All right, last lesson for Unit 9. So we are showing here a secant and a tangent, and in this lesson we are going to look at the segment lengths, not the angle formed by those segments, but the segment lengths. So the lengths of the segments created by secants and tangents are going to have a relationship. Let's explore that a little bit. Circle O shows secants PAC and PBD. Those are drawn there. And we know that PA is 3, AC is 5, PB is 4, BD is 2. It asks us to just find the following products. I'll save you that multiplication, but we have all of these different products. If I multiply the segments in question, these are what I get. And so the question is, which pair of products is equal, and how would you describe this product in terms of the segments? All right, so if you look at those, you can see that the two equal ones are here. And so I'm focusing on PA times PC, right? This product here and this product here. Well, if you locate PA and PC, PA and PC are on the same line. Here's PA here, and PC goes the whole way across that secant. All right, and then PB and PD do the same thing. PB is the outside part, PD is the total. Okay, and so what that's telling us is that the product that we're looking at is the outer segment times the total segment along a secant line. And if we do that, we will get equal amounts. So, now that just, before we go any further, notice I did not say the outer times the inner. The outer times the inner is not what I'm looking at here. The outer times the total. This total is 8. This total is 6. It's 3 times 8, not 3 times 5. 3 times 8 is the same as 4 times 6. So it's outer times total, outer times total. All right, so to formalize that, the product of a secant and the segment outside the circle is equal to the product of another secant and the segment outside the circle. All right, so the segment length theorem states as follows. The length of one secant with the length of its external segment, that's another way to say the outside the circle part, is equal to the product of the length of the other secant with the length of its external segment. Let's just keep that in mind as we go forward with the rest of these. Diagram of circle O, AB is 6, BD is 2. Got that labeled. AC is 4. Trying to figure out the length of CE. In order to use this theorem, I have to make sure that I total these up. We don't want to use 6 and 2. We want to use 6 and 8. And if there's one mistake that people make with secants, this is it. Do not use the parts, just use the outside and the total. So this one, the total would be 4 plus x. So I'm no longer concerned with the x and the 2. They've been used to generate the totals. Now what I'm going to say is that the first secant is 6 times 8, and the second secant is 4 times 4 plus x. Outer times total in both. So 48 on the one side, 16 plus 4x on the other. Subtract the 16, I get 32, and x comes out to 8. And is that what I wanted? Yes, CE is x, so I'm done there. All right, so again, it's outer times total. So this can be extended to segment lengths created by tangents and secants. It's the same thing. It's still outer times total. The only difference is, in a tangent, the outer and the total are the same thing. So that's why you see a square here, but it's still outer PA times total PC equals outer PB times total PB. Same thing. It's just written a little differently. All right, circle O, it's tangent from A to the circle at point B. All right, so secant ADC is drawn. We've got that. Length of 12, we've got that. Ratio 1 to 3, we got that. So it's not 1 and 3 units, it's 1 to 3 ratio, 1x and 3x. Determine the length of AB. All right, so according to my theorem here, if this is x and 3x, can I figure out what each part of those is? I think I can, because x plus 3x equals 12. So that's 4x equals 12, and that means x equals 3. All right, so this part's 3. Total is 12. I don't even care that that's 9. That's not going to get used because it's on the inside. And so now let's put a different variable there, call it y for now. And I think what this is going to write now is that the outer segment 3 times the total segment 12 is equal to the outer segment y times the total segment y, or y times y, or y squared. This is 36, and so y equals 6. Okay, so the tangent behaves the same way as the secant. You just use the same segment twice because it acts as both the exterior and total. All right, both of those theorems can be proved, so we may as well take a minute to prove them. And in this exercise, we're simply going to prove the first one where it's two secants, but the tangent proof would work the same way. We're trying to prove that those products actually are equal to each other. So walking through this bit by bit, explain why angle C must be congruent to angle D. Well, angle C has endpoints at A and B. Angle D has endpoints at A and B, so they're both intercepting the same arc as inscribed angles, therefore they're half of the same arc and equal to each other. Why must the two triangles below be similar? Alright, well, if I have equal angles at C and D, I just need one more pair of equal angles. Where would that occur? Well, they both share angle P, right? And so I have angle P congruent to angle P by the reflexive property. I have angle C congruent to angle D because they are both inscribed on the same arc. Okay, and so using similar triangles, we can set up a proportion involving the segments that we were looking for. So recall it was PA, PC, PB, PD. So that's a different color. That's this one. That's this one. It's this one. And it's this one. So I don't, that's terrible. This one. Okay, so I don't care about BC. I don't care about AD. We're going to write a proportion with just those parts. So PC is between angles, the single and double arc angles here. PD is also between the single and double arc angles. So if I put the right triangle over the left one, PD over PC. Smaller segments, they go over each other as well in the same order. Cross product, I get the product exactly as I wanted it. So that's the proof. But as we continue to use this, it's outer times total. Outer times total, not outer times inner. Outer times total.